Okay, we're talking about line integrals of vector fields. And so the most natural way to kind of introduce this and conceive of it is think of an object moving along a path C. That's what I'm showing here is red. So this is the path C. Through a force field. So our vector field is a force field, meaning that given any point in the plane, there's an associated force. Okay, that could be like a magnetic force, or wind, right? So it could be like wind or magnetic force or something like that. So, or current in water. And you're moving an object through that force field, and so what are we integrating? We are going to integrate we're going to look at, so first of all, how do we define C? So how do we define a curve in the plane or a curve in space? How is it defined? By what? Or vector value function, right? So it's like RT, right? So it's a vector value function, RT. So given any value of the parameter t, there's an x component to the vector and a y component to the vector, and we put all those vectors in standard position, tail at the origin, and then as t varies, it sweeps out the curve. So this is like the tips of all the vectors in standard position that we get from that vector function for different values of t. So what this integral is going to, so we think about integrals as accumulation. So it's kind of like accumulating components of these vectors along the path. So it's like we're going to accumulate, we're not going to accumulate force, but we're going to accumulate, what are we going to accumulate? So let's see this here. So suppose at, so let's see, this point right here, I have this vector like this. So that's what we're looking at this point and this vector. And so if we're doing a line integral of this vector field and we're thinking of this force field, we're thinking of an object moving through, what we're really saying is how much work, right? Because it's going to be, this is a force at some particular, say, x1, y1. And as that object is moving this direction, there's going to be a component of that force applied to the object. So the object is moving along this red line regardless of the forces. That's the object is moving along that path. And then but the force is going to be pushing on that object, either helping it or hindering it. So what component of the force helps or hinders the object as it moves along that path? What component of the force? So you could be like vertical, horizontal, parallel to the curve, orthogonal to the curve. Those are possible directions. So what component of that force is going to help or hinder the object as it moves through? So it's one of those four that I said. The vertical component of the force, the horizontal component, the parallel to the curve component, or the orthogonal to the curve component. Parallel to the curve, right? So whatever part of that force is parallel to the curve is going to actually propel or hinder the object along the path, right? So let's draw that. So that looks like this. And then the orthogonal component is like that. So as the object moves along that path, the orthogonal component is going to do nothing to it because it's staying on the path. But the parallel component is going to, what? In this case, help it or hinder it? It's going to help it along, right? It's going to help it along. So what do we want? So we want the part of the force in the direction of the curve, and then what is, based on our r vector, what is the direction of the curve? So if I want to, based on r, if I want a vector that shows the direction of the curve, what vector is that? Okay, and so the direction vector, so if r is giving me the points on the curve, then what gives me the direction of the curve at any point? Remember? R prime, right? R prime of t was our, that's a set, another set of vectors that always points in the direction of the curve. So that's like dr dt. And so that's what? Dx dt, dy dt. So this is what? This is our little dr vector. Little dr vector. So I want as much of f that's in the direction of dr. How do I get the amount of f in as much as it's in the direction of dr? Remember that? Dot product, remember that? That was our dot product meaning. So what I'm going to accumulate here is I'm going to accumulate all the forces along the way, but dot dr. And that's going to give me little amounts of force from the force field always in the direction of motion along the curve. And what is, this is like a little distance, right? So I've got force dot distance. So what does that calculate? Force times a little distance. That's work, right? So this is a little bit of work, dw. So it's, what is this? Then the whole line integral from, say, so this is t0 to t1. So what does that accumulate? It accumulates all the bits of work, what? That the force field is doing on the object as it moves through on the path. So it's the work not done by the object, but it's the work done by the field on the object as the object stays on the track.
So the tricky part looks like to be getting like a function that expresses how f will change along that curve C.
Well, we'll be given the force field. We'll be given the vector field.
Okay.
So we don't have to come up with that. So that's a given, right? So the force field that we're in is a given. And then, so what you will have to figure out maybe is you might have to figure out what the vector function of the path is. It might say it's a circle with radius such and such centered here. So you have to come up with the r function. Or it's a line segment from this point to this point. Then you need to come up with the r. But the vector field would be given.
What happens when the work done is greater than the acceleration of c?
It's independent. See, so the object is going to move the path, regardless of the force field, but it's going to get help from the force field or pushback from the force field, and that's what we're calculating by the line integral.
Okay.
So it doesn't matter if it speeds up, if it slows down, it accelerates. It doesn't. That's irregardless. So this is the work, the accumulation of work. Done by the field. This is important. On the object. So let's predict for this one. If we're starting up there in the upper left and ending up with the lower right, will the net work done by the field be positive or negative? So what's happening along here? Is the field helping or hindering? Helping. What about through here? Helping. What about through here?
Kind of helping.
So kind of helping, and then what about right through here? Not helping at all, because vectors are orthogonal to the path. And then what about the end? Helping a little bit again. So the net accumulative effect here is that the vector field is helping along this path. And whenever it's helping, that's positive work. Whenever the vector field is helping the object, that's positive work. If the net result was pushed back, then the value of our line integral will be negative. That means that in some places it could be positive, other places negative, but if the overwhelming amount is pushed back, then the overall integral will be negative. But if the balance of the work is helping, pushing along, then it'll be positive. Okay, so what do we need? Like I said, what do we need to do? We'll need to make sure we have our vector function of our curve defined correctly. We worked on that in the first couple of weeks. And then we're going to set up this integral, but then we're going to write this integral to solve it. It's a single integral, so it has to be in terms of t. So we have to write our vector function in terms of t. And what is dr going to be? So according to what I wrote here, dr will be, if dr dt is dx dt dy dt, then dr equals
Gradient.
dx dt, but it's not gradient because it's a path, right? dt. So that's for our dr and our integral, we'll use that. And that puts everything in terms of t. We have a single integral, we can solve it in terms of t. Okay, questions on the concept of a vector, a line integral of a vector field? Okay, so let's, that's kind of the overview. So let's look at example here. What do I want to do first? Let's try this one first. Okay, so here is, this is the path y equals x squared. Oh, I might as well do red here for the path. So C is according to y equals x squared from -1, 1 to 2, 4. And then my vector field is 2 cosine t, 3 sine t minus 2. What are vector fields, I guess. Oh, I'll just call it v, I guess. V xy is no, that's not right. That's not right. No, this is the vector field. Sine y1. Okay. Okay, so if we're going from -1, let's talk through what we predict the value to be. So we're going to start here. This is -1, 1, 2, 2, 4. So at the beginning, what about through this first part here? Positive, negative, or very close to 0? He said negative. Agree? Yeah, kind of going against the grain here. So like a little bit negative through here. What about right down here at the bottom? Zero, right? So about zero. So a little bit negative here. And then what about this last part? Pretty strongly positive through there. So we expect the value of this integral to be positive. We got a little bit of negative and then more positive. So when we do this line integral of this vector field over that path, we're going to expect to get a positive result. So let's set it up. Here we go. That's our. So we're doing f dot dr, right? F dot dr. So yeah, what would be? This is just f. So our vector field is f. Okay, so say, and that's going to be from something to something. So f is sine y and 1. Dot dr. But to get dr, we need r. All right, so we need to parameterize this curve. And what's the most natural way to do that? If I've got y equals x squared, it's not, remember, if it's circular, the natural thing to do is, remember? Sines and cosines. Here I just have a function of x that's not circular. Y is equal to x squared, so we have that that very helpful technique of just make x equal to t, and then y will be. So that's the parameterization, the natural parameterization for y equals x squared, t and t squared. And so then we need dr. What's dr? So it's the derivative of each component with respect to t. So 1, 2t, and then dt. But we need to get our force function, our vector field, in terms of t. Everything needs to be in terms of t. So we got sine of what? Sine of t squared, comma, 1 dot dr. What was dr? 1 comma 2t dt. And that from starting value of t to ending value of t. What's the starting value of t? It's the same as x, right? T is starting value of t is our x coordinate. So we go from -1 to 2. All right, and then we do our dot product, and we get sine of t squared plus 2t. And in most rigged problems in academia, you'd be able to do this by hand, but sine t squared does not have a closed form antiderivative. So we're going to use the computer to do this for us, and we're expecting what to be the case here? Positive, right? We were expecting positive by the visual. Okay? But in your homework and in the textbook, these will be rigged so that you can do antiderivatives here. There's no closed form algebraic antiderivative of that. But we're in the 21st century. We got awesome technology, so we should use it, right? So -1, 2, sine of t squared. Better get some parentheses going here. Plus 2t dt. Positive 4.11, which we predicted. And had we gone the other way, we get equal and opposite work, right? So negative work means What does negative work means? It means that so negative work means that the field is hindering the object so that the object is doing work back on the field, right? It's like the field is receiving work from the object because it's trying to stop it. Okay, so that's what negative work would mean. Questions on this example? Okay, so now let's do it. Let's look at a different one here. Same field. What happened to my pretty graph there? There we go. So same field, but I want to do this one. But that from 0 to 2.5, I think. Yeah. So now I've got the same field. Sine. Sine y1. And I have RT is given. And it is 2 cosine t, 3 sine t minus 2. Okay, and then t is going from 0 to, so this is actually t equals 0 down here. And this is 2.5 over here. And I want to calculate the line integral of that. So, what do you think about this? Positive or negative line integral? So what about it first? Positive through here, zero-ish through here, and then negative. So what do you predict? Yeah, maybe close to 0, but maybe positive. It's looking like there's a little longer stretch of positive there than the negative, but in the negative, it's like most of the component of the vector is really in the direction of the curve. So it's really up for grabs. All right, so I want you to set it up. So I want you to set up the line integral, and then I doubt that. Yeah, this is not going to be one that's fun to do by hand. So we'll put it.
You equal the theta. Okay, so then sine cosine constant loss appears. So but
Oh. Okay, so it looks like, what do we got here? Sine of 3 sine t minus 2. And that times negative 2 sine t. Plus, is the second part easier? Just 3 cosine t? From 0 to 2.5? Did I set that up right? And what did we say? Close to 0 but positive. We were good, right? So very smaller positive value close to 0. Okay, so I think what we're going to do in recitation tomorrow is what I've normally done in a lecture before. So we're going to get it started today, and then you're going to finish this thing in recitation tomorrow. So let's start. Here we go. We're going to look at, well, actually, let's do one more example before we do that. So here's a vector field, xy, 1 minus x. And I want to find the line integral of this vector field if C is the part of the circle with radius 2, centered at the origin, from 2, 0, counterclockwise to negative 2, 0. So we'll set this one up. And let's talk about this, whether we think this will be negative, positive, or close to 0 first. So what about towards the beginning here? This part here? So we're going from 2, 0 to negative 2, 0. So in this first part, is it strong or weak, positive, negative, or 0? Weak negative. Small vectors, but definitely opposing travel, right? Opposing travel. So this whole thing is kind of like weak negative. And then what about through here? Zero-ish, yeah, zero-ish. And then yeah, definitely zero-ish through here. Then what about the end? Stronger negative, right? So we expect the line integral to be? Negative, yep. So negative on the way, some 0 in the middle, more negative at the end. Okay, so we're expecting a negative result. And so here we've got to set up our own parameterization. The curve is not given. So what's the natural parameterization for this curve? Yeah, use cosine for x component, or x, yeah, and sine for y component. Our radius is 2, so and then our vector field is given, so we're off to the races, right? We need dr. What's dr? These are little direction vectors along the curve, right? These are all parallel to motion. Dr vectors, the parallel to motion. So can you set up the integral? T goes from what to what? T will go from? What's my T down here?
0 to pi.
You want 0 to pi. Agree? Yep, if I'm using sine t, cosine t, then t is angle measure, right? So we go from 0 to pi of x component of the field is xy. So that will be? I'm going to start my abbreviations here. C and S for cosine and sine. I think it's a nice trick, just as long as you're in context and you know what you're looking at. Okay, so for CT, ST, and 1 minus dot negative 2 sine t, 2 cosine t, dt. Did I set it up right? And I'm gonna do the dot product and have it solve it for me. So this might be one that you can. This is one that you could do with Calc 2 techniques. You got basically sine squared times cosine. That's like the chain rule, right? That's like reverse chain rule. And then 2 cosine t, that's doable. And then 2 cosine squared, use the half angle formula for cosine squared, if you remember that from Calc 2. So this one would be take a little time, but you could do it by hand. And that's going to be typical of the problems that you'll have. But we'll, for time's sake, we'll just put it in here. So what do I have? Negative 8 cosine sine squared, right? Check my math. Then
Plus 2 cosine t minus 4 cosine t squared.
I think I agree. And what do we expect again? Specifically? Negative 2 pi. Would be a very good guess. If it came out to negative 6.28319, I think a pretty fair guess is that exactly if you did it by hand, you'd get negative 2 pi. Okay, questions on this one? So let me just set up the what you'll do in recitation tomorrow. So we're going to do some what's called circulation line integrals. A circulation line integral is where you make a circuit and you start and stop at the same place. And you're going to be doing that for these two circuits. And then you're going to actually do it for these two circuits in this vector field and then these two circuits in another vector field. So you've got actually 4 vector fields to do. So let's talk about the triangle. Well, we've got a couple minutes here. So I'm going to do let's do a clockwise loop around the triangle. So how would we compute this, what we call a so this is a circulation integral. So when you have a circulation line integral, you can put a little circle in the middle of your integral, and that means that you're integrating around a closed loop, like the triangle. And so what would it take to do that? So what would that process look like of calculating that circulation line integral around that triangle? What's that? A lot of tiers? How many tiers? So what will the structure be to calculate this? Structure of that? 3 integrals, right? So calculating the line integral along here is a totally different path than this. So I'm going to need, say this is going to be C1 plus C2 plus C3. And then for something like this, on this diagonal, so just to keep it straight, so you could use, this is say C1, and this is C2, and this is C3, and you could use a different variable in each. So for C1, you could use T. For C2, you could use vector or parameter U, and for C3, parameter V, and then that just, you can use T for all of them, but just using a different vector can kind of just help you know what you're working on at the given moment. But how do we parameterize this? So one technique is, so this is the point 1, 1. And this is the point -1, -1. So a helpful technique is set the starting point of your segment to t equals 0 and the ending point of your segment to t equals 1. And then you can make your parameterization the other way around? No, right. So this is x start or x initial. I could do x initial, I guess, better. So this is a technique you can use for a line segment that forces the starting point to be 0 and the ending point to be 1. Do you see that? So by putting your initial value of x here and your final value of x here, if you plug in t equals 0, then you get x initial. That goes away. If you plug in t equals 1, then that goes away and you get x final. But this is a linear function, so then for all the t values between 0 and 1, you generate all the points in between. So this is a nice nice technique, because for a line segment, there's like an infinite number of ways you could parameterize that. Okay, you could make xt and do y as a function of t, but I think this is nice because then your t always goes from 0 to 1.